Electrochemistry, I don't need to read this to you. You can see the definition up there for you. Right? I want to focus on what happens with reduction and oxidation. That's what electrochemistry is all about. Just to remind you, when things get reduced, they gain electrons, and when things get oxidized, they lose electrons. And let me just flip to what's here written on the very bottom. One does not happen without the other. Okay? We describe them as separate reactions because it's very easy to see what's happening separately, what's being oxidized and what's being reduced. But they never happen in isolation. If something's being oxidized, that means something else got reduced, and vice versa. Now, as an example, let's go to a reaction that we've done many, many times, mostly in Gen Chem 1, where we take some zinc and put it in an aqueous solution of copper sulfate, copper 2 sulfate, and we end up with solid copper and a solution of zinc sulfate. So let's just show what's going on here. So here's your beaker, okay, and you've got some aqueous solution in there of copper 2 sulfate. Let's see. How do I want to do this? Here's some copper 2 sulfate in aqueous solution. Anyone remember what color that is? That's that really, really pretty deep blue color, right, that you use many, many times. Hopefully you remember this, right? And then you took some zinc, which is solid zinc, which is usually kind of grayish black, and you put that in here, and what happens? It gets clear. Sorry. I can't really do clear on here. Here, whoops. Let's do yellow here for clear, right? It gets clear, but what happens to the color of the solid? It started black as zinc. Anyone remember what the color of the solid is? What's the color of copper, solid? Yeah, orange, it's red, like a dark red, all right? So you end up with the solid copper in here, okay? That's what this is. This is the copper solid. Now, we can describe this reaction following the ions, right? The full ionic and the net ionic equation. Do you remember that? All right. Let's do that real quick, just as a review. So we can describe the full ionic equation, which is all of the materials that are actually there in solution. Right? That starts with zinc, solid, plus, now this is copper 2 sulfate. It's in aqueous solution. So we then show those as ions in solution, copper 2 plus ions and the sulfate ion. And then the reaction has copper solid, plus now we have zinc sulfate in aqueous solution, so we show those as ions. Zinc 2 plus in aqueous solution and sulfate ion in aqueous solution. That's the full ionic. And then we look to see if there's any spectator ions in here. Are there any spectator ions? What's the spectator ions?
Sulfur.
Peroxide? What?
Sulfur.
That's not what it's called, but yes. Sulfate ion. Yes, the sulfate ion. Anything else is a spectator? I'm losing my words here. What do we mean by spectator? They're present both in the reactant side and the product side. They're spectating. They're not actually involved in the reaction. They're there in solution, and when we show this is the molecular equation here, or the chemical equation. So we have sulfate ions there, but in this reaction that we're describing here, sulfate ions aren't involved at all. They're just swimming around in solution. They start in solution and they end in solution, so they're not doing anything. Everything else, though, changes in some form from the reactant side to the product side. So there's only one spectator ion here. And the rest, then, is what we call the net ionic equation, net being what's actually happening in the chemistry. that's going to be zinc solid plus copper 2 plus in aqueous solution is changing into copper solid and zinc 2 plus in aqueous solution. And from there we can describe something's being oxidized and something's being reduced. Now you normally don't show this, but I'm going to show it to you now just for emphasis. Okay? When you have metals, solid metals, as you find them in nature, they're neutral. That's why we don't have anything written in the upper right-hand corner for the zinc. But I'm going to go ahead and emphasize that's neutral. There's a 0 there. Same for copper. There's a 0 here. If we had gases, that's how you find them in nature. If it's elemental gas in nature, right, we would have that as a 0 as well. Okay, so we can now describe what's being oxidized here. The zinc or the copper? Zinc being oxidized. So oxidized is loss. So zinc is losing electrons. It's going from 0 to 2 plus. If it loses electrons, that means there's more positive charge than negative charge. So we can describe this as an oxidation half reaction. And what's being oxidized is the zinc solid 0 is being oxidized to zinc 2 plus, and here are the 2 electrons that are lost. And we can describe the reduction half reaction. So if zinc is being oxidized, then the copper must be reduced. So the copper started as copper 2 plus in aqueous solution, and it's gaining 2 electrons to give us copper solid. And I'm writing all of this in the same direction. I'm not switching things around. So, like I said, we're describing the individual half reactions, but really these happen at the same time. So we need to make sure that we obey the law of conservation of energy, or conservation of mass, whatever. And we need to make sure that not only are the atoms or the nuclei balanced, but also the electrons as well. So we have 2 electrons. One is on this side, one's on that side of the reaction arrow, so we can cancel those out. And we get to our net ionic equation, which is zinc solid plus copper 2 plus goes to zinc 2 plus copper solid. Just what we want. All right, now, that was review, okay? Now, when we set this up, the big question is, why does this reaction arrow go to the right? We've spent the whole semester pretty much looking at equilibrium reactions and things that go both forward and reverse, as well as some reactions that go in one direction. This goes in one direction. It is not an equilibrium state. The question is, why? Why does it go to the right and not to the left? What do you think? Class. Yes, you need to know what the answer is, but let's discuss why it is that case. It's all about stability. It's all about filling the valence shell. And you can look at that with this little number up here, which you can barely see because when I zoom it in, it's all pixelated. These are called reduction potentials. We're going to be talking a lot about reduction potentials. But yes, it has everything to do with stability. Reduction is really the driving force of this reaction. The tendency to want to gain electrons. Now, what you learned in Gen Chem 1 is that, yeah, if you're on the right-hand side of the periodic table, you're going to gain electrons to fill up your valence shell. In doing so, you are in the atom is in its most stable electron configuration. Now, to really understand that, you have to learn about effective nuclear charge and why is it that it's stable. And I addressed that in one of those videos. So if you're not familiar with effective nuclear charge, it's not the most straightforward concept. but it does explain all of these trends, including the tendency to gain electrons. So we have two choices here. Right? The reaction is either going to go to the right or go to the left. In this case, copper has a greater, for lack of a better term, desire to gain electrons than zinc does if they're in competition with each other. And we can see that in this table as the reduction potential, which is labeled as E naught, right? Now in this case, it's not a zero charge. This is not NaUGHT, which basically says we're under standard conditions. And we'll talk about standard conditions in a little bit. Right? This is the tendency to gain electrons. And it's going to be measured in volts. And the larger that number is, the greater the tendency is to gain electrons. And if you look at this table, both of these are written as reduction potentials. These are all reduction potentials. So this would be a reduction half reaction, and this would be a reduction half reaction for both the copper gaining electrons and the zinc gaining electrons. But you can see that the reduction potential for copper gaining electrons is greater than the reduction potential for zinc gaining the electrons. So in competition with each other, the copper is going to win. The copper is going to gain those electrons and not the zinc. Meaning that the copper is going to get reduced, not the zinc. But if the zinc doesn't get reduced, what has to happen to it? It gets oxidized. You can't have one without the other. Okay? But the driving force here is the tendency to gain electrons. Why the reaction arrow goes one way or another. That's the driving force. That's what I mean by the driving force. Let's just say the one with the higher reduction potential will get reduced. Meaning that the other one will get oxidized. Which means that we have to take that reduction equation, that reduction half reaction, and turn it the reverse, make it an oxidation reaction. So this one gets reversed. This would then become zinc solid. Will go to zinc 2 plus 2 electrons. In this example. Now we can think of all sorts of examples here, though, not just this one. I used this one because I thought that everyone would remember this reaction. Here's a table, actually this is a table that I made from various tables in your textbook. This is just a partial list of things that can get oxidized and reduced. And it's organized based on the reduction potential. So this is all a table of reduction potentials, all of these. Meaning that these all are going to be reduction half reactions. And for every single one of them, we have a reduction potential, E naught. It's also listing how many electrons are being gained here. Although we'll be looking at that later. So, for example, let's find the two that we were just looking at here. Here's the copper. 2 plus 2 electrons goes to copper solid. That's reduction half reaction. And here's the zinc. Zinc 2 plus 2 electrons goes to zinc solid. They're both listed on this table as reduction half reactions. And as such, we have what the reduction potential is. This one is positive 0.342 volts, and this one is negative 0.672 volts. Now, a little word about the positive and the negative here. There really is no positive and negative. That's just an artifact from the way that this is designed, and we have an arbitrary standard that's been set. And the arbitrary standard that's been set is right here. It's sort of bolded, but it's hard to see, so I'm going to just highlight it here. This is called a standard hydrogen electrode, or SHE. Standard hydrogen electrode. And all we've done is just set that as our standard, which means we're setting that to 0. But it's all the same as what I've been describing. It's just the tendency to be reduced when you are in competition with another metal. By setting that as 0, that means some of them will be positive and some of them will be negative, depending on what their tendency is. But ultimately, what we're going to be looking at is the difference between them. And I'll be showing that to you later. But let's define a few things here. So let's look at the copper. Right? We already determined that the copper is reduced. But because copper is being reduced, it's causing the zinc to be oxidized. Now, these are just the terms, okay? It's a little confusing, so just remember. Copper is what's being reduced. It forces something else to be oxidized at its expense, which means we call it an oxidizing agent. Spell that right. Oxidizing agent. It causes something else to be oxidized. Now that won't always be the case, because copper is over here. In the example I showed you between copper and zinc, copper is the oxidizing agent because it's causing zinc to be oxidized. And we can use the same terms backwards. We can look at the zinc. Zinc is being oxidized, which means that something else is being reduced. Now I'm going to put this in quotation marks. Well, not yet. This is what we then call a reducing agent. This is in quotation marks. Causes something else to be reduced. But as I've just been explaining, it's not causing something else to be reduced. The driving force here is the tendency to be reduced. That's what's causing something else to be oxidized. Okay. This is just part of the definition. It does get confusing, but people use it all the time, so you need to understand what these terms mean and how to work with them. So let's talk about this potential a little bit. All right, so we took a look at the copper 2 plus is being reduced to copper solid. And we have what that reduction potential is. That's going to be 0.342 volts. And we took a look at the zinc, right? If zinc was being reduced, it would have a reduction potential of negative 0.762 volts. But it's not being reduced, it's being oxidized. So the zinc solid is being oxidized to zinc 2 plus plus 2 electrons, what do you suppose the voltage would be on that? We took this value, right, but we're reversing this. Positive. It'd be positive, but the same magnitude, just in the opposite direction. So this is a positive, and this is now going to be a positive. Here, let me emphasize, this is just a symbol for an electron. This becomes a positive 0.762 volts. Because we reversed the reduction potential, right? Reversed the reduction potential. Now it becomes an oxidation potential. Not really, I don't think that's a term. Okay? But what we've done is we just reversed the sign. The magnitude stays the same. So if we were to add those up, we would find out what the overall potential for this reaction would be. Add these up, what do we get? It's like 1.104 volts. Now that might seem confusing to you, but let's go back to this idea of the sheet, the standard hydrogen electrode. Remember, that's just an arbitrary standard. If we just look at the difference, so here, our delta. What's the change that goes from 0.342 to negative 0.762? It's going to be that number, 1.104. That's all we're really doing here. It's just hard to see when you do all the math this way. All right, which is why I like showing it to you here on this nice table. All we're looking at is what the overall voltage potential is going to be when we mix these two together. It's all really about the reduction potentials. So here's the lithium down here. Let's zoom in on lithium. It's listed here as the weakest oxidizing agent, meaning that when you put lithium metal in competition with any of these other metals, it's not going to get reduced. It will always get oxidized. Meaning that it's the strongest reducing agent. Remember those terms, they're kind of confusing. Weakest oxidizing agent, strongest reducing agent. So lithium as a solid is the strongest reducing agent. When mixed with something else, it's going to cause something else to be reduced. But again, it doesn't cause. Those are the quotation marks. Right? If we look on the other side of this table, here's fluorine. You all talked about electronegativity before, right? Fluorine's the most electronegative atom that there is. Now remember, electronegativity is in the context of the electrons in a shared covalent bond. But it's all the same idea, right? The effective nuclear charge and the desire to gain electrons. Fluorine, in the upper right-hand corner, is going to have the strongest attraction for electrons in competition with anything else that might want to get reduced. So fluorine is going to be the strongest oxidizing agent. It will always get reduced when you match it with any of these other reactions. So this one's always reduced. The lithium is always oxidized. To you now, because when we're talking about this reduction potential, it's just that, it's potential, okay? And a good analogy to understand this is a waterfall, I think. So if we take a look at a waterfall, here, let's move this over a little bit. So here's our waterfall, okay, with water coming over here, and it's coming down the waterfall into the pool here. How far that waterfall drops from top to bottom, that's our potential. It's like potential energy, right? So the volts, think of the volts as being the distance that the water drops. So you walk up to that waterfall, and whether it's a 5-foot waterfall or a 100-foot waterfall, it's not going to hurt you until you're at the top and you jump off, right? That's kind of a silly way of saying that the volts themselves don't hurt you. What's running over this waterfall, though, that's the water. Okay? If we imagine, let's say we put a little water wheel down here. I like putting water wheels in my examples, right? So the water goes over the waterfall, it hits the water wheel, and that turns the axle that runs the machinery in the shed or whatever, sawing logs or grinding oats or whatever, okay? What's going to make that water wheel spin faster?
Is it the current?
It's the current. But what's the analogy here? What's the analogy of the current in this waterfall? It's the water going over the waterfall. Okay? So the more water that we have going over the waterfall, the more energy we can get out of that water wheel. And the analogy here, it's the current, it's the electrons, that's what current is. It's the electron flow, that's the current, over the waterfall or over the voltage potential. That's where you get your power from. I mentioned that we're going to talk about delta G at some point here, and I want to introduce it to you now. Yay, it's free. This is the useful work. Well, we're talking about work here. So look at this equation. You have a negative sign here. We'll talk about that later. And this is going to be the moles of electrons that are flowing through our circuit. E naught of the cell, right? That's going to be the voltage potential. Of our cell, right? That's what we were just talking about here, the E naught, right? The reduction potential, voltage potential. And then F, we'll talk about this in a little bit. This is called the Faraday constant. And the Faraday constant basically tells you how many electrons there are or what the charge is per mole of electrons. And actually the units that we use for that is in coulombs, not in amps. Okay. Here, right? This all comes from this one example that we've been using. But when we put the metal in the beaker and it turns from black to red, and the solution goes from blue to clear, that's what's happening. But we can't harness that energy. We can't harness that delta G in this reaction. We calculate it, but we can't measure it. We can't use it, I should say. The way we use it is by separating these two half reactions into two separate places and then force the electrons to go from one place to another place. And in that flow, we're basically then going to be able to harness this waterfall. That's what we mean by E of the cell, the reduction potential of the cell. What we're doing is we're going to separate the two. Here's the same reaction. All right? We have an oxidation half reaction over here. And we have a reduction half reaction over here. But now they're happening in two separate chambers that are connected. And in that connection, we can follow the flow of electrons. Because here we have two electrons are being lost, and here the two electrons are being gained. And so we follow those two electrons are going from one place to another. That's the same as the electrons going from here to here. And we have the water wheel to harness that energy. In this example, we have a light bulb, right, to show that as the electrons flow through this circuit, really, we're able to use that energy to light the light bulb. I'll try to even color code this. So on the left, we've got some definitions, the anode and the cathode. I'm not going to write this for you, it's right here on the slide for you. The anode is where the oxidation half reaction takes place, and the cathode is where the reduction half reaction takes place. Let's just focus on those two right now. So copper is being reduced. So we'll have copper 2 plus zinc solid is going to copper solid plus zinc 2 plus. Just to remind you of what we're looking at here. So the anode is where the oxidation is occurring. You can remember that by just vowels and consonants. Right? Anode, oxidation, those are both vowels. Right? Reduction and cathode are consonants. So you can remember it any way you want. You get a 50-50 chance of getting it right. Okay, so here is the oxidation half reaction. The zinc is being oxidized to form zinc 2 plus. So here is the anode. The anode is the actual metal. There's your zinc metal. Okay. The cathode is where the reduction is happening. So copper ions are being reduced to form copper solid. And here's your copper on the cathode. Now we also need to have some ions in solution here. We need the spectator ions, or some ions in this case. Let's just put in this case we used sulfate in the example. So we'll put sulfate in here, and we need a cation as well. You'll see why in a moment. So I'm going to put some sodium sulfate in here. Doesn't have to be sodium. Could be anything. We need some kind of a cation in here as well, and you'll see why in a moment. But for now, let's just put the let's just look at the ions that we're interested in for this actual reaction, the net ionic reaction. Because it's the net ionic reaction, that's really what's happening, right? There's no spectators present. So when zinc is being oxidized then, here's zinc 2 plus ions in aqueous solution. And notice that it's 1 molar, because we're working at standard conditions here. So when it's in aqueous solution, it's going to, I'm sorry, I'm going backwards. Zinc is being oxidized. So here's zinc solid. Here, I need a different color here so you can see it. Here's the zinc solid, and it's being oxidized. So it's going into solution to form zinc 2 plus in solution. And it's leaving those electrons behind. So here are the 2 electrons. Let me write this arrow a little bit better for you here. So as this reaction progresses, what's happening to the zinc electrode? Is it gaining mass or is it losing mass? It's losing mass because the zinc solid is being turned into zinc ions in solution. So at the anode, right, this metal is losing mass. Let's take a look at what's happening at the cathode. The cathode, we have copper ions in solution, and they're gaining 2 electrons to become copper solid. So where did those 2 electrons come from? Well, they were here in the electrode to then form copper solid when the copper ion in solution gets onto the electrode. So I guess I should put an arrow here showing that the 2 electrons were lost from the zinc as well when it went into solution. So what's happening then to the metal on the cathode? Is it gaining mass or is it losing mass? It's gaining mass. Okay? No different from what we've been doing on the board, except now we're showing it actually separated. So, for this to work though, we have to have some kind of a flow. We need to have a circuit. Because those 2 electrons on the right, on the cathode, that allowed copper 2 plus to get into copper solid, they had to come from somewhere, and we know that they came from the zinc being oxidized. So we have a circuit where those electrons then flow from one side to the other, and you can see that already shown here on the slide. Those 2 electrons go from the left side to the right side, completing the circuit. Now in this case, we have a light bulb in the middle of the circuit to show that there is some power there. There's some energy that's produced. We can calculate that energy, all right? That's your delta G. Remember, E naught, that's a voltage potential. It's not energy, it's just a voltage potential. All right, so we need to have a circuit here. Otherwise, what we have is a flow of charge going from one side to the other, and it builds up very, very quickly, and it will stop. If we connect the circuit, if we keep the charges overall neutralized, then this will keep going and going and going and going. So in order to do that, we use a salt bridge. And the salt bridge allows us to connect the two solutions of the cells. Basically, this allows us to neutralize the charges. And it's using spectator ions. Although they don't have to be spectator ions. They can be any ions that are not involved in the actual reaction. I mean, I guess that is technically the definition of what a spectator ion is. So, in other words, what we're doing right now is we're moving negative charge from the anode to the cathode side. Right? So if we have a buildup of negative charge on the right, we need to equilibrate that negative charge. So we need to have some negative charge going backwards. So in this case, if it's sodium sulfate that's in solution here, what ion would be going back on this red arrow into the anode side? What spectator ion would be going there? You want to bring negative charge back. Sulfate, that's right. The sulfate ions will go back into solution on the anode side because we've taken that negative charge away via the electron. We also then need to neutralize the charge on the cathode side because we're putting negative charge in there with the electron. So we need to bring some positive charge in there. So the sodium ions in this case would be going into the cathode side. Without having that connection, you won't get any energy out of the cell. Right? It needs to have the charges neutralized so that overall you can complete the circuit and have the charges neutralized in the end. And you'll actually be demonstrating this when you do this in lab. We have some electrodes set up and some voltmeters, and you'll be able to see what happens when you have a salt bridge there and when you don't have a salt bridge there. So the salt bridge itself doesn't contribute to the energy that you can get out of here, but it allows the process to happen. One more term to tell you about is the electromotive force. That's just a fancy term for what we've just been talking about. The electrons moving from one side to the other gives us a force that we can get some work done from it. All right, so now let's put this in the context of the equations that we were doing before. Here we have the oxidation reaction, right, for the zinc. And remember that that's going to be the reverse of the reduction potential, okay? So here the reaction runs in reverse of the reduction potential. Reduction. So we simply take the value that we read from the table, which isn't up here anymore, but that was negative 0.762 volts. And then we have the cathode side, that is reduction, all right? So here we just take the value that we read from the table. The reduction potential was, for copper, was positive 0.342 volts. And we can easily then calculate what the E naught of the cell is. Right? The E naught of the cell is going to be equal to whatever happens at the cathode and particularly what I'm talking about is the reduction potential of the material being reduced. And we're going to subtract that from the E naught of the anode. Because remember, the anode is the reduction potential of the thing that's being oxidized. You know, that sounds kind of counterintuitive because there's just reduction potentials. There's no such thing as an oxidation potential. But let me just write this for you, okay? This is the reduction potential of material that's being oxidized. Okay? But we have the negative sign in here. The negative sign will reduce that, will flip the sign on whatever the reduction potential is. It's just what we've been talking about. Reverses the sign on the reduction potential. I'm just trying to explain it to you a different way with a lot of words. That's probably confusing you all the more. It all goes back to, we're just showing the difference between the potentials. And it gets confusing because of the way that we've set the arbitrary standard for the hydrogen reduction potential being 0. Putting the negative sign in there and doing it this way is just one formal way for you to just plug numbers in and calculate it. Or you can just do it on your own by recognizing what's being reduced and what's being oxidized. You get the values from the table and you just take whatever's being oxidized and you reverse the sign because you know that that reaction is going in reverse from the reduction. So this is not about just finding the right equation and plugging the numbers in, all right? You have to really think about what you're doing to understand why this equation is working the way it is. One more thing to show you on this slide is a shorthand, because we don't want to have to draw this all the time, okay? So we have a shorthand that we use for this, and the shorthand looks like this. We have 1 bar, 2 bars, and 1 bar, and that shows you the separation of the two cells. And by convention, we have oxidation on the left and reduction on the right. And then we have the electrodes, the anode and the cathode, those are on the far sides. So that means we'll have the anode here and the cathode here. And those are both solids. Those are the metals in their solid form. So we have the solid anode on the left and the solid cathode on the right. And then in between we have what they are in aqueous solution. So whatever the anode metal was, here it is in aqueous solution. And whatever the metal cathode was, we have that in aqueous solution. So to show that to you then, in this example, with the copper and the zinc, we would have, zinc is the anode, so we would have zinc solid, and then zinc 2+ in aqueous solution. And then the double line is just separating the two cells. And then in aqueous solution, over here we'll have the copper 2+ in aqueous solution, and finally the copper cathode. So it's a convenient shorthand. Okay, so that was one full-on discussion example. Here's another one. And let's not worry about writing this is from the textbook. Let's not worry about writing all of this stuff. Let's just cut to the chase here. So we've got two things going on here, copper and aluminum. So what's going to be reduced here? Why the copper? It's a higher reduction potential, okay? So the copper is going to be reduced. So let's write this. Copper will be reduced. So let's write that reduction potential. So copper 2 plus is going to pick up how many electrons to be reduced to copper solid? 2 electrons form copper solid. And the reduction potential for that, E naught is, E naught, that's a superscript. E naught is positive 0.342 volts. Right, that means that the aluminum is going to be oxidized at its expense. So let's write what the half reaction for the aluminum oxidation. What do we start with on the left-hand side? Aluminum what? Solid. Very good. Thank you. So we start with aluminum solid, and it's going to lose how many electrons to become the aluminum cation? 3. So this, actually, the arrow goes over here. It forms aluminum 3 plus ions in the aqueous solution plus 3 electrons. And the E naught, well, the reduction potential, if it were to go the other way, the reduction potential is negative 1.1662 volts. But we're running this one in reverse, negative 1.1662 volts. Okay? Which means that this really is going to be positive 1.1662 volts. So we can calculate what E naught of the cell is now. If we were to hook this up and measure the energy, or at least, if we were to hook this up and measure what the voltage potential of this cell is, not the energy, but the voltage potential, what would it be? Positive 1.5082. Okay, volts. That's the voltage potential. So we know how to do that. Now let's do something that this problem isn't asking us for. Let's look at how much energy we actually can get from this cell. Okay. Remember, we also know that delta G is equal to minus N times the Faraday constant times whatever E naught of the cell is. So we need to figure out how many electrons are flowing per mole of this reaction. How many electrons are transferred when we do 1 mole of this reaction? How would you figure that out?
Balance it.
Balance it. All right, let's balance it. How do you balance this? You can balance it a couple of ways. How would you balance this? What do you want to balance? I mean, the nuclei are balanced, right? We have 1 copper over here and 1 copper over there and 1 aluminum here and 1 aluminum there. So the nuclei are balanced. What's not balanced here? The electrons aren't balanced. How do we balance these electrons? Lowest common multiple. What's the lowest common multiple between 2 and 3? 6. So we multiply this one by 3 and multiply that one by 2. We'll then get 3 copper 2 plus 6 electrons will give us 3 copper solids, and 2 aluminum solids will form 2 aluminum 3 plus cations plus 6 electrons. Now it's balanced. Right? And if we were to cancel these out, we would get the net ionic equation, which is 2 aluminum solids plus 3 copper 2 plus goes to 2 aluminum 3 plus plus 3 copper. Now that's the net ionic equation, right? I'm not showing you any spectator ions. We can invent any spectator ions in here we want, I suppose, right? We could do 2 aluminum plus 3 copper sulfates go to 2 aluminum. Now in this case, it would have to be aluminum sulfate is written that way. That's if we had everything in there, okay? And I just used sulfate. We could have used anything for a spectator ion. It's a spectator. It doesn't matter. This is the net ionic. So what we've learned from this is that 6 moles of electrons are transferred. So if we want to find out how much energy is there, here I wrote delta, but it should be delta G. We need to now just plug this into the equation. So what are we going to use here? So delta G, here let's use a different color here on top. Delta G is equal to negative N, that's the moles of electrons. So how many moles of electrons do we have? 6. Times the Faraday constant, which is 9. Yeah, I always get this one wrong. 9.56 times 10 to the 4th coulombs per mole, and E naught of the cell. So do we just plug this number in there? We do. What, plus 1.508 volts. Now you may be wondering, look, we just did all this to balance the electron, okay? Why didn't we change what E naught of the cell is? And I'll just leave you with this thought, okay? E naught of the cell is the drop. It's the voltage potential. This hasn't changed at all. This never changes. When we're calculating the energy we can get out of it, it's the flow of electrons over this drop. The flow of electrons will change depending on how many electrons are there. But the drop, the voltage potential, is always the same. So when you do these calculations, you just calculate what E naught of the cell is, right? Regardless of balancing it, because there you're just looking at what the reduction potentials are. When you balance it, that's when you need to figure out how much energy can you get from it, because that's completely dependent on the moles of electrons that are flowing through that system.